This is, in essence, a Y-delta transformer. The Y-connected primary provides a neutral for the delta system, and this is solidly grounded. The delta secondaries of the transformer are connected in series. This is called a broken delta. One side is grounded like this, and the other feeds a ground over voltage relay. If no fault exists, there is negligible voltage across the relay because the balanced voltages produced in the secondaries cancel each other out. Now, in the case of a ground fault on one of the lines, the voltage to ground on that phase is reduced. This reduces the voltage across the primary of that phase. This will cause a reduction of voltage in the associated secondary. Hence, a residual voltage will appear across the ground over voltage relay to cause operation. Additionally, indicating lamps can be placed across each secondary, thereby giving indication of which particular phase is grounded. Now, at this point, let's briefly summarize the methods of grounding which you will encounter. Solid grounding. This is the case with most utility systems above 40 kV. Generators may be grounded through an impedance so as to limit the magnitude of fault current. Non-grounded systems are sometimes used in industry where a continuous power supply is required. Distribution systems are sometimes not grounded, and in this case, ground fault detection equipment must be installed. Delta systems can be grounded with grounding transformers. Safety grounding is essential. All equipment in power stations, substations, switchyards, and so on must be solidly connected to the ground mat. Now, at this point, let's take a break. Please switch off the videotape and thoroughly review this material in your workbook. Earlier, we examined the different types of fault that can occur on the power system. Any one of these faults could happen in equipment such as transformers or generators or even circuit breakers. But more often than not, faults take place on transmission and distribution lines as they are more exposed. Now let's take a closer look at the effect of these different types of faults. To do this, we'll need to study the associated phasor diagrams. Here we see the simple three-phase system functioning under normal, balanced conditions. The circuit has been simplified by removing transformers and breakers. The neutral is solidly grounded in order to anchor the system voltage. This phasor diagram shows the phase relationships and magnitude of the line-to-neutral voltages. Line-to-line voltages are also shown. Note that the voltage between lines A and B leads the phase voltage VAN by 30 degrees, and similarly with the other phases. This we already learned in a previous tape. Now, let's see what happens if a short circuit occurs across all three phases at the end of the line. Referring to the phasor diagram, we see conditions at the fault location. In studying these fault characteristics, it is usual to consider that there is zero load current on the system, so only fault currents are indicated. This set of phasors also represents a three-phase to ground fault. The line voltages are drastically reduced, but they still maintain the same phase relationship. The system is still balanced. The magnitude of line current increases greatly, and it is lagging by approximately 60 degrees on its respective phase voltage. Why is this? Well, this angle is determined by the nature of the system impedance to the fault. That is, the generator impedance and the line impedance. the line impedance predominates, and for a 115 kV transmission line, this is usually about 60 degrees. High voltage lines, 230 kV and up, may have impedance angles as high as 85 degrees. Conversely, low voltage distribution lines usually have a line impedance angle of about 50 degrees. Well, now let's move on to look at the conditions for a phase-to-phase fault. In this case, the short circuit is between line B and line C. If you could place a voltmeter between lines B and C, you would find the voltage to be much lower than normal. Similarly, the voltage between line B and ground would be lower, as is line C to ground voltage. The phasor diagram shows this. The short circuit drastically reduces the difference in voltage between lines B and C, that is, VBC. This reduces phase voltages VBN and VCN, and the angle between them to less than 120 degrees. This causes a change in the phase relationship of VAB, which is the voltage between the lines A and B. As we know, this is the difference between VAN and VBN. Subtracting these phasors, we find that VAB moves back in phase angle. It now leads VAN by less than 30 degrees. The magnitude of VAB is also reduced slightly. We can see that this phase-to-phase fault has seriously distorted our previously balanced condition. Now let's look at the line currents. As we are considering zero load, IA is 0. The current traveling through line B is feeding the fault, and this will lag by approximately 60 degrees on voltage BC. Once IB passes through the short circuit, it returns along line C. So current IC can be shown at the same magnitude, but 180 degrees apart from IB. Incidentally, there is an easier way to construct this phasor diagram, first by indicating only the phase voltages line to neutral. Here we have VAN, VBN, and VCN. Both VBN and VCN have been depressed in magnitude and phase angle due to the short circuit between line B and line C. We can show the voltage between line B and C like this. Similarly, VAB is the voltage between VAN and VBN, and in the same manner we can construct VCA as the voltage between VCN and VAN. The currents go here. IB is at an angle of 60 degrees to VBC, with IC the reverse of IB. Yet another common fault is the two-phase to ground. This example shows a fault between lines B and C, which in turn is faulted to ground. We have currents IB and IC flowing to the fault, and IG, the ground current, leaving. Thus, IB plus IC equals IG. The resultant phasor diagram is similar to that for the phase-to-phase fault, except the depressed voltages VBN and VCN remain at their pre-fault phase angles. The current in line B and line C lags by a large angle, and this is complicated by the fact that some fault current is flowing to ground. Now here we see the conditions at the fault location for a ground fault on line A. The voltage between lines B and C remains normal, as do also the line B to ground and line C to ground. This is not so for line A to B and line C to A. In both cases, the voltage is reduced due to the fault on phase A. the voltage between line A and ground is drastically reduced. It could fall to zero if the fault impedance is zero, but usually ground faults do contain some resistance, and therefore a small voltage will remain. The ground current will be high, as it is limited only by the impedance of the line and the return path to the grounded neutral. The flow of fault current through the ground path will actually cause a volt drop and a consequent rise in potential of the neutral at the source. This potential shift may be quite small, depending upon the actual grounding arrangements. As before, we are considering in this example that the load current is zero. Therefore, currents IB and IC would be zero, and they are not shown. At this point, let's quickly summarize the types of faults that we have discussed and their main effects. First, let's look at the three-phase fault and three-phase to ground. At the fault location, the voltage will fall close to zero, and very heavy fault current will flow in all three phases. As in all cases, the magnitude of current is limited by the total impedance of the circuit, plus the impedance of the fault. In the phase-to-phase fault, the magnitude of the voltage between the two shorted phases at the fault will fall close to zero, and a heavy fault current will circulate in those two lines. In the phase to ground fault, the voltage will fall in the two faulted lines.